This is the mark scheme for the winter mock exam that was taken in December for Year 1 Computer Science. So going through this paper then, we're going to go through question by question to work out what the answers are and how we arrive at that answer. Question 1 is converting hex number A7 into denary. So we need to take A and 7 as two hex digits. A in denary is 10, 7 is 7. These are then converted to the following 4-bit numbers. So 10 would be that, and 7 would be 0, 8, 1, 1, 1. So we've taken each hex digit as an independent value. We've worked out what that is within denary, and then you need 4 bits per hex digit. So that gives us the number in binary. To work out the number in denary, we'll have 128 plus 32 plus the 7 we've got from this side. This gives us the number 167, which is the answer. There are 2 marks awarded on this, 1 for working out the binary and 1 for then hex. You can gain 2 marks for showing the process in the final answer. The next question is asking us to represent the denary value 7.625 as an unsigned binary fixed point number, 4 bits before and 4 bits after. So therefore we've got 8421, we've got a binary place, and we've got 0.5, 0.25, 0.125, 0.0625. So for 7 we've got no 8, we've got 4, we've got 2, we've got 1, dot, and then to get 625 we've got 0.5 plus 0.125. If I just remove these, and that is our final answer. You get 1 mark for the first 4 bits and 1 mark for the second 4 bits. If you didn't put the dot in there, that does not matter. Next question related to an 8-bit 2's complement binary integer, which means the most significant bit would be negative. Now there are 2 ways to do this. We can either continue to add on to negative 1 to 8 till we get minus 18 by doing minus 1 to 8 plus 64 and so on, or we can follow the 2's complement law. We put our numbers 1 to 8, 64, 32, 16, 8, 4, 2, 1, and 18 would be 0, 0, 0, 116, 0, 0, 1, 2, 0. So that is equal to 18. To get this into 2's complement, up to and including the first one, we leave as is. There we go. And the rest we flip. Bring this back to show those transposed. Up to and including the first one from the right hand side, keep as is, and then flip the rest. That therefore equals minus 18. Remember, with a negative 2's complement number, the most significant bit is minus 128. So if we tried this out, minus 128 plus 64 plus 32 plus 8 plus 4 plus 2, that will give minus 18. Next question, what is the largest possible denary value that can be represented using 8-bit 2's complement binary? Let's take these column headings again. Well, if we have a 1 here, it's going to be a negative number, so that needs to be a 0 for it to be a positive number, which means that will be the largest positive number, which is 1 less than 128. So the answer is 127. Describe how 8 bits 2's complement binary can be used to subtract one number from another. First, write both numbers as a pure binary equivalent. E.g., you can then put this down as an example and put 24 as a binary number and 48 as a binary number. 48 is being subtracted, therefore this would need changing into its negative version. We can say how, using 2's complement, and then demonstrate how. Once the number to subtract is converted into negative form, this is added to the original, or to the first number, using binary addition. And again, demonstrate. So 23 would be, when you've worked out minus 48, that gives you, and adding them together gives you that, which is equivalent to minus 25. So you must describe, it is asking for a description, you must describe as well as make sure your descriptions tie in with the example numbers given. The next is the finite state machine. If we look at the first one's been done for you. So we're inputting a 0. So it shows the output produced by the finite state for some possible inputs. Some of the outputs are missing. Input strings are processed out with the rightmost bit. So that's the important part there that I nearly just missed, and it's the most common missed part of that question. So let's have a look. Starting from the rightmost bit, we've got a 1. A 1 gives an output of a 1. And then, look what's going on here. If the input's 0, the output's 1. Input's 1, output's 0. And we're going to remain in state 1. So we've got a 1, which becomes 0. 0, which becomes 1. 0 becomes 1. 1 becomes 0. And the rest of the zeros become 1s. What's happening next? Well, if we can look at this one, this has got an example, 2 zeros. Well, a 0, look, we're staying in state 0 with the output as a 0, and that has happened there. Then we've got a 1, which gives us a 1, and then there's this flipping over. 1 becomes 0, zeros become 1s. Here, let's follow this through. So the first input is a 0, which gives an output of a 0, and we're still in state 0. After that, we've got a 1, which gives us a 1. After that, we've got the 0, so zeros become 1s and 1s become 0. So we end up with that situation, and that is the number that we end up with. Okay, you may be able to spot the pattern. This one starts with a 1, so we've got an output of a 1. Next is a 0, 0 is 1, so going through we end up with this number. What is the purpose? It gets the 2's complement of the binary value that's input. So it's converting a positive binary value into a negative equivalent. And I want you to then complete the unshaded parts of the table. So if the original state was S0, we input 0, the output is 0, and we end up in S0. If the original state is state 0, and we enter a 1, we end up in S1. So the other parts of this table to complete, if it's a 0, the output's a 1, and 1, the output's a 0. We end up in S1. So that is that table complete. Okay, that is question 1 of the mock exam.